So good morning. I'm very happy to present also one of the speakers. It's not my task usually, but I'm very honored. I need my glasses. So Claudio Persello came from Netherlands, from the University of 12. Claudio received the laurea, the bachelor, and then the master degree in telecommunication engineering, and is a PhD in Communication and Information Technology from the University of Trento, that is in Italy, in the north. Before joining the Geoinformation Science and Earth Observation Department of University of 12, he was a Marie Curie Research Fellow. Marie Curie is a very particular program conducting research activity at the Max Planck Institute for Intelligent Systems and the Remote Sensing Laboratory of the University of Trento. His main research interests are in the context of machine learning, deep learning for information extraction from remotely sensed images and geospatial data. The activity includes investigating and developing dedicated deep learning techniques for various remote sensing sensor data and multiple applications, focusing on the societal and environmental challenges. He is particularly interested in combining deep learning and Earth observation to address and monitor the progress towards the Sustainable Development Goals. Claudio is a referee for multiple journals and a program committee member of several conferences in the field of remote sensing and image analysis. He is associate editor for IEEE Transaction and Geoscience and Remote Sensing, member of the editorial board of the ISPRAS Journal of Photogrammetry and Remote Sensing, and MDPI Remote Sensing. He served as publication co-chair for IGARS 2021. He is a chair of the Image Analysis and Data Fusion GRSS Technical Committee, and his PhD thesis was awarded the prize for the best PhD thesis on pattern recognition published between 2010 and 2012 by the GIRPAR, the Italian branch of the International Association for Pattern Recognition, and is a senior member of the IEEE, and is also the chair of our IADF technical committee, okay? A big clap to him.
Thank you very much, Silvia, for this very comprehensive introduction and for the nice words for me. Thanks a lot. Good morning. Good morning, everyone. And as you heard, so I have a particular interest in using Earth observation for addressing the Sustainable Development Goals. That's what I'm going to talk about today. I will give you several examples of applications that can contribute in that direction to monitor the progress and possibly to help achieving these ambitious, very ambitious goals. So let me just start with a quick question. Who is familiar with the Sustainable Development Goals? Okay, I think it's about 1/3 maybe. Okay, so that's good because the other 2/3 will probably learn something new, and I think that's nice. So what I'm going to talk about is several applications, and the work I'm going to present is usually the result of collaboration with several colleagues, with my PhD students, so that's what usually makes research possible. I guess this might be even not necessary, but I usually start with a very quick introduction about why do we need machine learning in Earth observation. And I guess if you are here, maybe you already have a hint why we do that. And let me just take the opportunity to emphasize that, well, we have more and more Earth observation data available, collected from different sensors, different platforms. And more of these data are really openly and freely available, thanks, for instance, to the Copernicus program of the European Space Agency, and also the NASA archive of Landsat that is also fully open and free. So we have more and more data we acquire daily information about our planet, resulting huge amount of data. So I think only the Sentinel program collects, don't remember the exact number, but more than 10 or 20 terabytes of data every single day. So what do we do with this? Well, in principle, this is very valuable information to understand what is the health status of our planet, just to put it in simple terms. Then on top of that, we have a lot of other geospatial information data sources collected by people, by citizens, using smartphones, using various technologies. And we have other geospatial data of different forms, so we can combine all this for having a better understanding of our planet. So the challenge is indeed, how do we process, how do we analyze all this huge amount of data in an effective, efficient, scalable way? So that's where, of course, machine learning comes into play. And deep learning, especially in the last few years, we have seen great advances in this technology. And this allows us typically to extract information from this data, fusing maybe different data sources to extract useful information. What kind of information? Well, typically the product may take the form of maps, 2D maps, land cover, land use maps. These are very common type of maps. But that's not restricted to that. So sometimes we have very specific type of maps, crop type maps, or forest type maps, so that where individual tree species are classified. Or you can think of other things like cadastral maps, which are very important for land administration, and I'll talk about that also more later on. Do you think there are other, just to ask a quick question, there are other forms of representing geospatial data that could be useful for several problems, so to say? So maps are useful, but maybe there are other ways to represent geospatial data. One can have 3D models, for instance, right? So that's not only, these are just example 2D, well, one can have also 3D models. 3D models of city, 3D models of forests, and so on. Now, a very hot topic in the last few years is digital twins. I don't know if you have heard of that. So I don't have this in the slides, but just wanted to mention this. It's a very hot topic. So the idea is to not just represent reality with a static map that just captured that instant, but a digital twin is supposed to give a real-time representation of part of the world, so to say. Originally, this was applied to more industrial engineering, for manufacturing, and so on. But more and more is becoming a big topic also in geospatial applications. So I'm currently very much interested in, for instance, city digital twins. And the idea is then not just to map things, but to produce a tool that represents reality and allows to take decision and have this feedback between the reality and the digital twin. So it's a very interesting topic. I just wanted to mention that. But the topic that I would like to talk about today is more related to the Sustainable Development Goals. Why? Well, because among the many applications that we can think of for Earth observation data, some that I think are particularly valuable are those that can capture and can help us understand better global phenomena. So of course we can have very detailed images and make studies at the level of individual city, individual region, and so on. But because satellites capture information from the whole globe continuously, we can also use that information to study and get a better understanding of global societal and environmental phenomena. And, you know, the Sustainable Development Goals are indeed a blueprint of actions that we need to take collectively as a society to try to address some of the most pressing global problems. And here I would like to just focus on some of these problems where Earth observation can play a role. Of course, some of these problems are a little bit outside what can be done with geospatial data, but it's actually interesting to observe how remote sensing can be helpful for many of these problems. So actually, I will talk about problems like ending hunger globally. It's still a very big problem. So food security, and that's connected to SDG 2, Sustainable Development Goal 2. I will talk about sustainable cities and communities, how to make our cities more livable, more sustainable, and how, yeah, remote sensing can help us towards that goal. I will talk about tenure security. I'm not sure if this is a term that is familiar to most of you. Does anybody know what I mean with that? Yeah? You want to say? Very good. Exactly, exactly. Thank you very much. I will have some slides on that later on, so I will talk about this. But tenure security is indeed an important aspect to allow people to have recognized, registered rights for the land, for the houses where they're living and they own. And then there are many other applications that can contribute to climate change, so that's climate action, SDG 13, and more on biodiversity aspects, life on land, SDG 15. So if you want to have a look, I have also, I've done a paper a few years ago with colleagues, international colleagues, on kind of reviewing what deep learning can do towards these goals. And actually, many of the examples that I will talk about today come a bit from this paper. But I want to do a step back, because I remember when I asked who is familiar with the Sustainable Development Goals, there were only a few hands raised. So let me just try to give you a little bit of an introduction of that. So it's an agenda. It was signed in 2015 in New York at the General Secretary office in New York. And the idea of this agenda is to have a plan of actions, and all member countries that signed this agreed to provide data information to track how well they are doing towards achieving these goals. The idea is to reach, and it's a very ambitious goal, is to reach peace, prosperity, and a more sustainable world by 2030. That's coming quite close, right? And yeah, I guess we are still lagging behind for many of these goals. But I think it's important to realize what are the aspects that we need still to work on, right? And it's important, and that's one of the fundamental principles of this agenda with respect to previous one designed by the United Nations, is the principle that if you want to address and understand the problem, you need to collect data to keep track of how well we are doing in all these challenges. There are 17 goals. You can see them all here. And not only 17 goals, there are many targets, 169 specific targets, and 232 indicators. These indicators are typically very precise statistics that have to be collected by countries to report on how well they're doing on all these different targets. So it's really the first, what we can call evidence-based, data-driven decision-making policy that requires country to take seriously into account these challenges, collect data, and report on that. Good news for us, and I mean for us working in remote sensing, Earth observation, and geospatial technologies, is that about 34 of these indicators can be directly or indirectly informed through Earth observation and geospatial data. So that's the good news, at least to me. We can do something important with the technology, with the skills that we develop, hopefully also a bit in this summer school as well. So I think that's something important. I have to say that in reality, we still have to do a lot of work to kind of promote the use of Earth observation for this SDG. So there is, in the research community, there are papers, there are people talking about this, but not all countries actually, I guess maybe only a few of them, actively use Earth observation in their national statistics reports. So that's something we are working on, so to not just make the research, so that's my interest in general, it's not just the research, not just the development of the methods, that's of course important, but to make sure to connect the research community with policymakers, with governmental, non-governmental bodies, and make sure that this technology can be applied in practice and address real problems. Some considerations just to discuss a little bit. So the opportunity that I see is that combining Earth observation and machine learning, we can extract geospatial information in support of all this, or at least some of these indicators. And we can do this with reduced cost and time. And that's of course important because most of the UN organizes this according to per country. And each country has a national statistical office, which is an agency responsible to report to UN about these indicators. And typically they work with the collection of traditional method to collect statistics, household survey, census data, and so on. This takes a lot of time. They are expensive ways to collect data. And of course, using Earth observation and automating the process with machine learning, we can do things at a much larger scale, repeated at a higher frequency in time, and possibly obtain more accurate and more objective information. Another thing, results are potentially objectively reproducible in different countries with the same methodology. One of the challenges is that countries use different methods to report on the same thing, and makes often this indicator inconsistent if you look at them from different countries. So that's also another problem. Possibly the technology can make the statistics more consistent. Many challenges, so here are just a few that came to my mind. So we need to make machine learning more trustworthy or explainable in a way that policymakers and agency can really use this technology in real problems. One element that I find it's a bit not well documented in the whole agenda is data quality. So the agenda emphasizes the importance of collecting data, but in my opinion doesn't emphasize enough to report on the quality of this data. So it's okay to report a number, but if you don't tell me, I don't know, a confidence interval, what is the uncertainty, what are the, and all these actually measurements and indicators involve large uncertainties. So for me, it's important that if we want to make progress on this, we need also to be more transparent on reporting uncertainties. Another thing, it often requires interdisciplinary work. It's not like the kind of work that you do as a researcher, you go and work on your own. You need to connect with people, with different stakeholders, and so on. So that's challenging. It's not easy, but in my opinion, that's the way to go ahead if you want to make an impact. An impact is not necessarily publishing a paper, but make sure that the technology reaches the people that can benefit from it. And that's not easy. That's not easy. So what I'm going to talk about next is to jump into different areas, into different topics. I'll talk about different problems connected to different SDG, mapping smallholder farms, talk about deprived urban areas. I'll talk about the third one. It's actually a more technical topic. It's not connected to an SDG. But I will try to explain why this, at least in my opinion, is important. So how to extract or to map from raster images things in a vector format directly. That's something that can be directly incorporated into a GIS. Then I'll talk about mapping cadastral boundaries that's connected to tenure security, mentioned before. And last topic, it's about glacier mapping. So that's also very important for climate change. Good. Let's get into this. So the first topic, smallholder farms. So I'm not sure if you are familiar with what I mean. Smallholder farms are typically small-scale agricultural communities, farmers. And SDG 2 looks in particular to end hunger, achieve food security, improve nutrition, and promote sustainable agriculture. But target 2.3 specifically look at small-scale food producers. And why is that so relevant? So these communities are often among the most vulnerable communities. They typically are basically eating what they produce. So they fully depend on their agricultural production for their sustainability. And in many parts of the world, that's what's happening. A large part, more than 80% of cropland in Africa are actually cultivated by smallholder farmers. That's true also for many countries in Asia, in America as well. And unfortunately, we have very incomplete information about where are these maps, where are these agricultural fields, and how are they managed, and so on. So we have incomplete spatial information. And of course, what we can do with remote sensing is basically to map and extract information. But in a way, that's already very important, not maybe directly to the individual farmers, but more at the level of managing resources at regional level, at country level, to understand things. But this is also actually connected, and I'll talk about later on, about tenure security. Because if farmers do not officially own the land they cultivate, they are in a very vulnerable position. From one day to another, they can say, okay, that's not your land anymore, and they are deprived from their resource. And also, by not having legally registered rights for their fields, they cannot access to financial services, and they cannot access to insurance services, which are very, very important, right? Because if there is a bad year, there is no rain, there is no insurance to cover, then the farmers are in big trouble. And they cannot access financial services. That means they don't have the means to improve farming practices. And means these are typically agriculture cultivated with low intensity compared to fields to agricultural fields cultivated in Europe or North America, where a lot of technology is used, the latest fertilizers and so on. Those fields are much more productive. I'm not an agronomist, so I don't know all the details, but what I mean is it's important to collect that information. So a few years ago, I started working on the problem. Now I'm getting a little bit more technical. about delineating agricultural fields. So this was actually one of the key technical issues that was discussed in various environments, also in the GEO group, the group on Earth observation, and was actually agreed that obtaining information about the parcels of agricultural field boundaries is very important for many applications. There are countries where all these data are just publicly available. In the Netherlands, we have open geospatial data sets where there are all the fields. We have a GIS layer with all this information. We know what crop are there, and it's all open. But of course, there are many other countries where there is no data, and in that case, Earth observation can help us. Okay, let's get a little bit into the, this was more to motivate why this is relevant. Let's go a little bit more at the technical level, at the level of analyzing data and extracting information. How do we extract these agricultural field boundaries from images? So what we want to do, just I show you here an image, the panchromatic, the multispectral, and last is what we want to obtain in the end, possibly nice boundaries of all agricultural fields. If you look at this image, of course, this is just an example. In different parts of the world, field might look different. But I guess you can see how complicated the problem is, because not all boundaries are just clearly visible. In some cases, it's more like a change in a textural pattern from one field to another. So it's not really, you just detect contours, you just detect edges in an image. So there are many, if you're familiar with image processing, there are many filters for edge detection, right? We have tried them. They don't work in this case, right? So you would extract all the edges in the images, all these rows and the crops, but not the boundaries between different fields. So that didn't work. This was, by the way, based on a project that some colleagues in my institute, in ITC, were developing with fundings from Bill and Melinda Gates Foundation. And the idea was to map agricultural field boundaries in several African countries. And we have collected data, so actually they have collected data on the field. So that takes a lot of time, but we had data for training machine learning models. And we used those data for designing a deep learning strategy. So that's, of course, where I'm heading towards. Why? Well, because we have seen the traditional unsupervised image processing methods just don't work. This problem is way too complex. So I'm not going to talk a lot about techniques, but they are often the basis of the solutions that I'm going to show. I hope some of the other speakers talked about convolutional neural networks, right? So it's something you are familiar with. So what we have actually done, we have used one particular architecture. It's called SegNet. Now it was a bit old. Now we have newer architectures. But in principle, we use a fully convolutional network to perform sort of semantic segmentation. But it's not directly semantic segmentation. What we did, we trained this network to just perform a binary classification at pixel level and tell boundary, no boundary, right? So that's relatively simple, and that's the result you see on the top right. It's just, I can use this. So this is the result. So on one side, we were quite happy with the result because it really could capture pretty well the boundaries, but we were not entirely satisfied. And maybe you can have a look. I hope you can see also from the back. Why do you think that was still not good enough? Yes?
Most of the boundaries are not closed to, and there are many
Yeah, exactly. So this approach doesn't guarantee to have closed contours, right? So if we have gaps, then we cannot close and have, like, in the end, ideally what we want to have in the end is polygons, to extract vectors, extract polygons of each individual field. So that doesn't work directly. So what we did, we used another technique. You see only the acronym there. It stands for Oriented Watershed Transform. It's using the soft output from the network, so not directly the binary, but you can consider the probabilities or the soft outputs. And from there, it derives this other result, this other map, which actually contains closed contours. Actually, it's a hierarchical segmentation where the color actually indicates something like the strength of the boundary, and it's hierarchical. And then we used another algorithm, single scale combinatorial grouping, that takes this hierarchical segmentation and pick the best level of this hierarchy and finally predicts the closed contours. Results are not perfect, because if you look closely, sometimes to close the gap, the contours are not really accurate, but at least we have closed contours and relatively accurate. Yes, I think there was a question.
Yeah, my question is, are you considering validation to evaluate the errors?
Sure. So what we did, I think in the next slides I have something. Yeah, I will tell you a little bit. I don't have the results. Okay, I'll tell you. So we did this experimental analysis. We used this data set that is collected in Nigeria. Very complex situation because fields are really small. That's typically the problem. So it's very small, fragmented. So it's very different from how fields look, for instance, in Europe, where are larger, more regular in shape. So that's pretty difficult from the image analysis point of view. We have a training, so I'm not sure, the color is not the best, but the sort of green boxes are the tiles used for training, and the blue are the one for testing. So we actually trained the model and tested it, right? And all the yellow contours are the ones that have been actually collected on the ground with GPS and so on. So we did actually an experimental analysis. If you want to know more, actually, if you look at this paper, so in the paper you see that we have also a second data set. I don't have it here in the slides, but there is more on this. And here I just looked, in my slides I don't have the quantitative results, the numerical ones, just qualitatively, just to show you. These are the results of the 3 different steps, right, for these test tiles. So you see, first is just this sort of semantic segmentation, then the hierarchical segmentation, and the final result is on the bottom. As I said, this is just qualitative. Here more or less works well, but then we have some issues here and there. But if you look at the paper, you see the accuracies. I don't remember the number, but I think we use different metrics because one can just use metrics like for semantic segmentation and look at pixel level, compute precision, recall, F1 score. These are the typical metrics. That's what we have done. But also we have used other metrics that are used to really delineate the polygon in a vector format. I think I will tell you more later on this. That was like our first work in that direction. And somehow it was promising, but we relied on very high resolution images. Commercial data, expensive, not always easily applicable, large scale. So we thought, okay, let's see what we can do with open data. Let's try to use Sentinel-2 images. And the problem, of course, if you want to use Sentinel-2 is that the resolution is 10 meter. It's relatively coarse. So then, you know, fields are small, not always visible. So that makes things pretty challenging. So what we have explored is a super resolution contour detection. So the idea is to, you know, use a fully convolutional network that is trained to detect the boundaries. And you know, are you familiar with, that's an older architecture, but are you familiar with UNet, the type of architecture? Some of you is, perfect, good. So you know that in a UNet you have an encoder and a decoder, right? So and you have that branch that kind of downsampled the resolution with max poolings, step by step, and then you have the decoder that reconstruct the high resolution step by step. And one can do a similar thing, like adding one additional block in the decoder and actually go from the original resolution to higher level, so a higher resolution. So that's a similar idea here. So actually what we do in here, there is an upsampling layer. A little bit like the transpose convolution that you have in a UNet. And then you can use this to refine. So you have additional convolutional blocks to refine the boundaries at higher resolution. So you can have one or two of these upsampling layers. So you can start from 10-meter resolution, you get to 5, potentially to 2.5-meter resolution, and so on. So if you always go for a factor of 2. So that was actually a work of a master's student, so and it was a nice study in this direction. By the way, you can ask questions anytime. If there is any question, any doubts, or just let me know. What we are currently doing is we have a small project with the FAO. This is the Food and Agriculture Organization of United Nations. And we want to actually apply field boundary delineation to Asian countries, to Vietnam and Cambodia. Their situation, it's not so different from the previous one because fields are still pretty small. In this area, are mostly rice paddy. And we wanted to design a solution that takes open data, Sentinel-2 images to extract agricultural field boundaries. What was the main challenge? As often in these real problems, if you want to design deep learning method, is reference data. Just to have good quality data for training deep models. You know, there are plenty of data sets out there if you just want to do land cover mapping. There are hundreds. But if you enter into very specific problems like this one, then it's hard to collect good data for training and testing. So we developed, that was one of the things, we developed a benchmark. So we have collected several tiles. You see here all the numbers, 62 tiles spread across the 2 countries. We try to sample the diversity of different areas in terms of landscape and agricultural fields. And we actually hired a company, did a very professional job, digitized all the agricultural field boundaries in these tiles. A lot of work. 500,000 fields manually digitized, so it's really a lot of work. But now we have a very nice data set that we can use for training, for testing different models in 2 countries. So it's actually the purpose is to apply this large scale at country level. 2 countries. This actually, we asked them to digitize the polygons. So they are polygons of all agricultural fields. And let me also, disclaimer, so these are visually interpreted, right? So we don't say, we cannot claim these are in any way real cadastral parcels, right? So it's not something we say. They are just visually delineated agricultural fields. With uncertainties, right? Nothing is perfect, also because this is you know, sometimes it's a bit subjective. Is this really a boundary between fields, or is it's just a little footpath in between the fields? So there are uncertainties involved. But okay, in general, it's pretty high quality data set. Can be used for any other purpose in principle, but we used it for training deep learning models. The data is free, so if you look the paper, you find also a link to the data set itself. And this is kind of the pipeline that we used. It's similar to the one I showed you before, just we changed some of the blocks. We used a different network there. But we still had this multiple step approach, where you have something like a binary classification first, then you have to close these contours. This is a little bit different technique, but again, that's the problem. And then we have polygonization. So finally, we want to have polygons here. And then we can actually compare our results with the reference. We can assess how good that is, and we can extract different metrics. And yeah, what we did, we used several metrics at raster level. So as I said before, typical precision recall, F1 score, but also vector-based metrics. I don't think I have a reference here. It's a pity, but we use this metric. It's called polys. If you're interested, if you don't find it, I can look it up for you. But it's actually a metric that is comparing polygon in a prediction against a reference, and actually gives you a measure of how well they are matching with each other. It's something like the average distance between vertices in one polygon with respect to the closest boundary in the other one. But it's very good, because I think, and I'll tell you more, so I think it's important that in geospatial application we move towards workflows that in the end produce vector data. Why? Well, because we do a lot of raster image processing, but if you want to do something applicable in practice, most of the, I don't know, municipalities, the governments, they work with GIS system. They want to have a database, they want to have polygons. If you have polygons if you just have a raster map of where are the fields, what do you do with it? Not much, you just have a map. But if you have a GIS system, you have polygons of the fields, then for each polygon, you can attach attributes. You can attach attributes of crop type, you can touch things like expected yield, farming practices, possibly owner, if these polygons are indeed at least correspond with the cadastral parcels. So there are many advantages. So that's why we need, I believe, to move towards Earth observation. That we need to work on the link between Earth observation and GIS, to put it in. What are the challenges? I'm looking at the time. I'm not sure if I take more than needed, but that's okay. The coffee break is 10:30 or 11? Ah, okay, so we still have time. You tired? You're okay? Good. Challenges. Well, the spatial resolution, that's probably the biggest challenge. Because, I mean, if I apply this to the Netherlands, fields are big. Actually, that's what we did in the previous work. So fields are really nice, regular. Actually, in the Netherlands, it's all flat, so there is no physical constraint. They're just plain rectangles, all the fields, so it's simple. But in other countries, that's not the case, so things are actually pretty difficult. One can use very high resolution images, but of course there is cost. What we did, we did one thing, we just used Google Map images. In principle, those are free, but of course, only RGB, you don't have the spectral bands, you don't know for sure from which satellites. I mean, you know probably what are the satellites, but they're officially not supposed to be used for analytics, just for visualization. But that's what we could do. The other thing that I'm still working on, it's how to make sure that these polygons that we extract are accurate, but also topologically consistent. Because maybe that doesn't seem to be that difficult, but actually, if you have all polygons attached to each other, you want to make sure that the polygons that you extract are perfectly aligned to each other. You don't want to have gaps, you don't want to have overlaps, these kind of things. So, you know, if you want to have a high quality product in the end, that's not easy to do this in an automated way. And unfortunately, what I see that mapping agencies still do all of this manually. So that's the reality. Sometimes a bit sad because I do a lot of research on machine learning to automate things. There are fields, of course, where machine learning is used, but I am aware of several agencies. So, for instance, in the Netherlands, I will talk about later, but all basically the cadastre, it's digitizing and updating the cadastral map, but also a topographic map. And that's manually digitized continuously, because it's not just making a map once, but it's continuously updating it. So there's a team of digitizer manually delineating objects and so on. Any questions? Because that's kind of wrapping up this topic before I jump to the next one. Yeah. So there is no board here anyway. The difference between intersection over union or polis, this vector-based metric, the difference is, I mean, they are, of course, a related metric, right? So if you have very high intersection over union, probably you also have a very good vector. The problem is you might have an intersection over union that is, let's say, 98. It's 98%. It's pretty good, right? So if you think, okay, that's a very good thing, then you actually look at how is this polygon, and then you realize that you have corners with a lot of vertices. Instead of just a straight corner, you have 10 little vertices here and there. I don't know if you're familiar with GIS, if you ever... So then you realize that what comes out from the automated system are very dirty polygons, so to say, with lots of vertices which are redundant and so on. And you don't capture this problem in an intersection over union. You think, okay, I just take the raster and I polygonize. It's just a simple step, but in practice, it's not that trivial. And polys can actually capture also these little details. And it's not only polys, we used also other metrics. So a simple one is just comparing how many vertices you have in the reference and in your predicted polygon. Sometimes you have like 10 times more vertices because it's delineating contours which are not regular enough. I'll talk about more on this. Later we talk about building outline, extraction. It's, again, we want to do this with vector, and then that's typically a problem because you expect some regularity in the shape of buildings. What was the second question? Yes, so this was done in the Netherlands. This here, so you can have a look. This is also published. We used the dataset from Flevoland. It's an area in the Netherlands. So yeah, interesting. It's a whole island that 50 years ago was not there. If you want, I can show you, but I don't have it here in the slides. But it's the most simple case you can imagine. because it's that kind of thing I described before, very large and regular fields. Okay.
Can I have one more question?
Ah, yes.
I would like to, I wonder the really great job done in Africa and agricultural field, but I was impressed and I liked it, and I was wondering about the reproducibility of the research. Have you tried it in different areas? Does it work? Can it be applied? Because this probably would be very valuable for many other countries.
Yeah, indeed.
Is there an idea to do that?
So, it's a matter of often getting the funds for doing these things. And so we had this project with FAO, and with that we did this project for Cambodia and Vietnam, also because there was a donor behind. And it was interesting. So now we, apart from the tactical work, of course I cannot tell you everything, but basically within the project, we are also doing capacity building. So some of my colleagues will go actually to Vietnam, to Cambodia, and talk. So there is a company that is picking up the technique that we have developed and is supposed to make this operational. And they also do some sort of training for the organizations that are supposed then to apply this at national level there. We would like very much to apply this to other countries. So we have seen some studies in Africa. And, well, personally, I'm currently looking, there is a NISA project call exactly on the SDGs. And I'm, again, working to put together a consortium and to do this in other countries. So the idea is to really show the potential to really at the operational level and possibly for to use Earth observation for the national reporting on the indicators. And this is possibly very useful for many things, but it's a matter of often fundings. So we have a few contacts in East Europe currently, Poland, Hungary, and I'll talk in the next topic. We have also many contacts in Africa for other things. So we also want to explore this, how to apply it in Africa and potentially everywhere, but yeah. I'm pretty sure, and I know that there are also companies that are very much interested in this. We had contact with a bank in the Netherlands that was also very much interested. I will not tell you the name, but that's okay. Why, you think? Well, because a bank is actually offering financial and insurance services to farmers. So they are also interested in collecting this kind of data for them and in support of their clients, so to say, right? So yes, for sure we want to keep this. I think it's a very interesting topic, so we look for a way to have an impact with this. Are there more questions? Yes.
I was wondering about while listening, maybe extracting the boundaries between fields on an urban areas like informal settlements, as they have the same irregular pattern and narrow lines or dense streets between informal settlements.
Yes.
So do you have an idea if it is the same models can be applicable for urban areas, not only agricultural?
Not the same thing, but actually the next slide I'm going to talk about mapping informal settlements.
Okay.
It's not about cadastral mapping, but that would be very, very challenging. Because informal settlements are a really very dense area. If you want to delineate sort of cadastral parcels, that's very, very hard. I guess it's potentially possible with very high resolution images. Okay, then I'll move to the next topic, which is indeed on deprived urban area. I use this generic term to actually include terms like slums, informal settlements, or inadequate housing. I will maybe get back to these 3 different terms later. A little bit of motivation. So due often to rapid urbanization taking place in many countries, often in low and middle income countries, rapid expansion, rapid urbanization, often this results in very high inequalities in different neighborhoods, in different areas of urban areas, and often results to what we call slums or informal settlements. Often these are deprived areas which lack access to sanitization, clean water, in some cases other services like healthcare, education, and so on. But there is a very large variety and complexity behind all this. What is the other problem is that so you see here an example which is very clear, and there are several. If you are interested, it's a very interesting, you can just go to that webpage, Unequal Scenes, and you can see lots of pictures that really show you this large diversity. So you have in many cities wealthy and rich neighborhood, and just next to it a slum. Oh, it's a huge difference, right? So these are cases which are, let's say, pretty clear also from a picture, but there are also cities where slums are scattered in the city, and sometimes it's really much more difficult to capture where these areas are and so on. And the other large problem is often there is little or inaccurate or outdated information about the people living in this area. So often these areas are not reported in official maps. So you just don't know where are the slums, in many cases. Of course, there are the big slums that are very well known and everybody knows where they are, but there are other situations which are more complicated. So why is this an important problem? I guess you understand it's a societal problem. And looking at the predictions for the next years, urbanization is going to grow. In terms of proportion of people living in informal settlements, the trend is positive. Things are, in a way, getting better. But since the population is growing, actually the number of people living in these areas is increasing. Okay, connection to SDG. So SDG 11 is about making cities inclusive, safe, resilient, sustainable. Particular target 11.1.1 looks at access to adequate, safe and affordable housing, basic services, and upgrade slums. And the most specific thing is indicator 11.1.1, because it requires nation to report on the proportion of urban population living in slums, informal settlements, or inadequate housing. These are the 3 terms used by UN Habitat to define what I call more generically deprived urban areas. These are actually, if you look at, so UN Habitat, I'm not sure if you're familiar, is the custodian agency for SDG 11 and is the organization within UN kind of responsible for cities in SDG 11. And they also define what are these things. They also gave a definition of what is slums, informal settlements, and inadequate housing. But let's not get into this specific definition. Maybe I can comment on this later. The point here is we can use Earth observation to map where are these areas, to offer actually a more objective and realistic view of where are the slums and so on. So that's something with colleagues in my organization and outside we are working on. I now try to translate the societal problem into a technical one, because in the end we want to map these areas from Earth observation data. And it's a very difficult problem from a technical point of view as well, not only from a societal point of view. From a technical point of view, because the definition of what is a slum, it's not that crystal clear. As I said, there is a definition given by UN Habitat, and slums and informal settlements are different things, and that I think adds to the complexity, because, okay, let me try to explain very quickly. So, according to UN Habitat, slums are defined at the level of household data. So basically, they capture the deprivation of people. And to collect this data, you need to make a household survey. And to say whether it's deprived, you are actually saying people living in this area are deprived. And this includes also information about income, education, and things like this. Informal settlements is actually defined as an area level. So it's actually capturing the concept of deprivation of the neighborhood. And that can be better captured from an image. So, right, you can say this neighborhood is deprived. Not fully. So in images, you only see proxies of what can be a slum or not, right? But at least you can see signs of deprivations. Let me put it like this. You typically see very dense area, small, very small houses, roof material of poor quality, often lack of vegetation. So these are kind of the characteristics you typically observe in images. Then there are many other things that are just escape. You don't understand from an image whether the people living there have access to water, a proper sewage system, and things like this. Anyway, what we can do is to map according to visually observable characteristics of deprivation. Can you see in this example where are the slums? Huh? Yeah. It's written where is the picture. Would you be able to say within the image where is the slum? More or less. Yeah. Now, yeah, that's there. But, you know, this is a particular example. It's from Dar es Salaam, and cities are all different, right? And, but we can do something with this. So typically, we can use satellite images, and we can capture this. In the past, people have tried different types of techniques, object-based image analysis, the use of textural features, and so on. You can imagine I'm mostly doing deep learning a bit. The reason why it makes a lot of sense, especially here, is because you want to capture this spatial pattern, right? It's not just the individual pixel that tells that's a slum or not. You need to capture all information in the neighborhood. So fully convolutional networks typically work well. Now, well, a few years ago, I studied a particular architecture to map informal settlements, and we have done some tests in that was, I think, in Dar es Salaam and other cities. I think this maybe is a bit technical. Just to mention, I use this kind of approach based on dilated convolutional kernels. It's a little bit of an old concept, but it's still used in other networks. So the idea is to enlarge the spatial support or the receptive field of the network by kind of inserting zeros in between. That's the idea here. So if you have a 3x3 kernel, you could enlarge it with a factor of 1, 2, 3, and so on, just enlarging the filter. So it would still capture, let's say, a larger spatial information, but you don't increase the number of parameters. So that was the idea. Now we used a not too complex network, but I said this is 2017. So if you look at the pace of deep learning developments, this is Stone Age. And here are just some results to show what we obtained in a few study areas in Dar es Salaam. And you see just, we did a very simple comparison with other techniques like support vector machine and a patch-based CNN and the FCN DK6, that's the technique we were proposing at that time. Look, I have to tell you, these accuracies, and if you look at the literature in slum mapping and so on, you typically see, well, you have an 81 or more than 80% of accuracy, so that's very good. I have to tell you the reality that often you don't see in the literature, and I think it's a bit of a problem of our community. We publish results where we get good results. Where you don't have good results, you just don't publish. So you get you typically get a biased understanding of how good is a technology for a certain application. And people usually don't talk about this. I want to be fair, and I want to talk about this. Because people look at my paper, and I'm saying, I'm not accusing anybody, I'm accusing myself. But it's not only me, let me be clear. That we typically report things only when and where they work. And that's not only for this, it's true for many other applications. But anyway, now I will tell you what we are currently doing, and I can give you a better sense of whether the technology works or not. Because the problem is then you have calls, tender from the European Space Agency, and they say, now we have seen the technology works, apply it large scale, produce maps at country level. Yes, okay, guys, but it doesn't really work that easily. You see these results there because it's a little part of Dar es Salaam, and that's where it works. Doesn't mean I can produce large-scale results and accurate results. That's what we are currently working on. I will get to that point in a bit. Before that, actually, I have another thing to tell you. So the other thing is also binary maps usually don't really make justice of the reality, because slums can be very different from each other. There are some areas that through the time, gentrification, the idea is that they become relatively wealthy, not to say wealthy, but they have relatively good living qualities. And others that are really, really with very bad hygienic conditions and poor quality of life in general. So we try to understand things a little bit more specifically and characterize domain of deprivations, which can be financial, human, social, physical, and so on. So this was a work done by a master student a few years ago, but we are still working on that, but just to show some concrete example. So with the okay, that's not the reference I meant. Yes, this one here. So, Ajami, what was his first name? I forgot. But he was a very brilliant student, and we applied convolutional neural networks to map slums in Bangalore, in India. There, in that city, situation is that there are many slums scattered over the whole city, often small slum pockets here and there. So to produce map, it's challenging, and it's believed that the population living in slums there is largely unreported. So again, according to UN Habitat, there are nowadays more than, I think the current one is 1.1 billion people living in slums in the world. That's the current statistics. How accurate is that number? I cannot tell. So it's believed that often in some areas, just people are that's not registered, they don't come in the census officially, so we just don't know. But anyway, let's come back here. So what this student did, we applied convolutional neural network from satellite to satellite images to map slums, but not only slums, but also to assign what we could call a severity index. And at that time, I think we called a deprivation index. Actually, that's according to more the British kind of literature in defining deprivation. Okay, let's not get too much into the detail. What we did, we applied to, so what you see here is the boundary of the city of Bangalore. All these little dots are slums. And they are officially reported, so the municipality, that's the data they have in the municipality. So there are believed to be more than 1,400 slums in the city. We collected data, not myself, but colleagues that had a project on this, and they've done household surveys. That's the HH there. They visited 37 slums, and they have collected really detailed information, including things like education, income, and things like this. Lots of data, so lots of time spent in this effort. And we wanted to use this, so actually we use this to then construct an index that takes all these multiple factors of deprivation into account. So you can have multiple, and then you can try to aggregate everything into one number, one index. Complicated thing, but one of the major challenges is, well, in the end, what we wanted to do is can we predict not just binary, slum, no slum? Can we predict the index of deprivation? Yes, but the first challenge was, okay, but actually we only have 37 samples, which seems, is of course very few. On the other side, takes a lot of time because still. So what we did another survey that we called the quick scan survey, where a person went in these neighborhoods and just collected visual features of the neighborhood, and then collected this and aggregated into an index. So this is, of course, less accurate, but still gives an idea of the deprivation level. We used very high resolution images, Playad at 50 centimeter. We use a CNN. I don't, if you want, you can ask, but basically that's VGG type of architecture. And we initially, what we did, so how can we predict the deprivation level? We have only 121 samples. You still cannot train a CNN with 121 samples, to be clear. You usually need thousands of samples, right? So what we did, we used the slum boundaries of the official from the municipality, and we trained a CNN for the binary problem, slum, non-slum. And that already allows you, and those were more than 1,000, so we could train a CNN. And then we fine-tune the CNN to changing the loss function from a classification to a regression, and then we can regress the deprivation level, so a continuous value that tells the deprivation level. And this is the result that we obtained. So, what you see in this table are the R square of different strategies. So we actually use a combination of the CNN features, handcrafted features, and GIS. And GIS means features like a number of features. So all the details are in the paper, but collect a lot of geospatial, like distance to schools, distance to hospitals, and so on. So basically the geospatial information. Combining these things, the result was 75. So 0.75 in R square means that basically with this feature you capture pretty much, so 75% of the variability of the deprivation level. So I think it's an interesting result, so to say, that with this geospatial data you can capture pretty well this deprivation. Then we also extended this to extrapolate a map at the city level. Okay, so this is one study. I mentioned I wanted to then come back to what we are currently doing. So I'm working with colleagues of mine in ITC within a project funded by ESA, which is a specific project, that was the call, to use Earth observation in support of SDG 11.1.1, the one I showed you before. to estimate proportion of people living in slums, informal settlements, or inadequate housing. So what do we do in this project? We cover a large number of cities, well, large, 8, 8 cities all over the world. And we don't just produce maps, right? We involve local communities. We have contact for each of these cities with what we call a co-anchor, a person that is usually either working in a governmental organization, in a university, in a mapping agency, or so on. And through them, we get in contact with the community, also the slum dwellers themselves. And we use this project, we organize what we call living labs or workshops, where we have contact with the people, and we collect information about what kind of deprivation, what kind of challenges they face, and we also collect data to train models to then map informal settlements. So the idea is also what we kind of a motto, kind of is global challenge is local action. So it's a global problem, but we need to take into account the local context, different legislation, different culture, different concept. So I said there are UN Habitat definition of what is a slum. In practice, every country uses a slightly different definition of what is what. And you need to understand this. And in each city we do this work to understand how is the situation. And we use Earth observation data to map. Mostly we want to do this using Sentinel data because it's free and it's open. That's a little bit more the technical sort of workflow. So we have Sentinel data. We collect additional geospatial layers, typically to model access to services and so on. We need population density and this kind of information. We use AI, we use deep learning strategy. What we want to do in the end is to derive city scale statistics. So the 1111 tells me to derive a number that tells the proportion of people living in slums. That means I don't only need to map where are the slums. In principle, I need to know how many people are living there. That's definitely much harder than just mapping things. So we need to have a population density layer, which again comes with uncertainties. And then when you intersect population density with where are the slums, then you can calculate the proportions. So that's the strategy. I don't remember what I have in my next slides. Okay. This is what we call a user-centric and data-centric approach. It's also based on other projects. Idea Maps, Idea Atlas is the name of our project, and Idea Maps is a related one. So we interact. These are some pictures collected from some of these workshops. And again, it's not just a mapping exercise. In principle, we want to collect data that is also useful locally for people. Sometimes the dwellers themselves are very interested, and they can use sometimes geospatial data for their purposes. For if there is an eviction going on, they can use evidence to support that they were actually living in this area and things like this. So it is a complex societal problem, and it's hard to describe everything in a few slides. Another thing we are currently doing is, again, to translate this into something that works in practice, to collect data. How do we collect good data for training deep learning model and to produce maps? Where are the slums? The data from, as I said, from each of this country, each of these cities, we get data from some of these cities. Some of these cities are technologically more advanced, so they also have their official cadastral information and so on, but it's often incomplete and outdated. So what we do, okay, we ask the local community, help us in collecting accurate data. So initially we were just doing workshop and discussing, but that's very hard. So we developed a portal that we use to then, during this sort of workshops, do something like a mapathon, and we ask people now, can you delineate where are the slums and where are the non-slums? It's a time-consuming exercise, but I feel we need to be more and more aware of data quality in all these challenges. I see paper published on slum mapping, which and they maybe develop some new technology. From my perspective, it's not very useful if people just digitize by themselves what is a slum, what is not, with no connection with the people, with no connection with the country. I think it's not going very far this way. So to do something useful, we need to take care of data quality, we need to have interaction with the people, we need to do something that supports the people living in there. So, okay, it's a complex thing. What we do is this platform, we show our current prediction. We know that prediction is also not accurate because it's trained on inaccurate data. So how do we do? Ideally, in an iterative process where we show our prediction, we ask the local community, especially in areas where our reference tells something and the prediction something else. And that often happens, right? So then we have to understand, is it our prediction that is wrong, or is your reference that you gave me that is outdated? And that often happened in several cases. So we have sort of an active learning strategy to use our prediction, ask the local community to verify certain areas, and then they can confirm, is it really deprived or not? So that we can indeed improve and refine the quality of this data. So that's what we are doing. It's a very time-consuming process, but that's a way we can collect data that is meaningful. And GeoVille is the company that works with us, has developed this platform. I'm honestly now very much interested in expanding this platform for multiple applications. So this is tailored for the problem of mapping informal settlements. But I'll talk about different applications today. I see more and more the need for a platform that allow researchers, people, to collaboratively work on curating high-quality data sets. As I said, we have plenty of data sets out there for standard problems. Land cover classification, land use classification. But if you go to specific problem, and often, that's maybe my opinion, they are the ones that are more interesting. So mapping informal settlements, delineating agricultural fields, cadastral mapping, these kind of things. You don't have high quality data there. And if you would have a platform that allows collaboratively to digitize and with the mechanisms to verify quality, and then potentially run the models, show results, and allow to, again, correct potentially inaccurate labels and so on. So that would be something that I'm very much interested to put forward. I can talk more if you are interested on this, but let me see. I'll try to finish this part. So coming back, so we use this approach to collect data, refine data, and potentially we will have several versions of these data sets in each of these cities. We train a CNN, that's the kind of strategy. We try different architecture combining Sentinel-2 and Sentinel-1, also SAR and optical. And it's a lighter version of a unit. In my experience, I've worked with Sentinel data for many things. You typically don't need unit or network with all these downsampling blocks, so lighter versions are typically good enough. The resolution is not very high. One thing that we did, and I think it's relevant, is to also predict the density, the built-up density. So in Sentinel data, you don't really see much. You don't see individual buildings. What you capture is the built-up density. That's kind of thing that is visible there. So we are also using a strategy that allows you, that's not visible there, but to predict the slum map, but also to predict the built-up density. Good, these are so these are the results we obtained with the first version of our data set. And that's, maybe you remember I said, most of the results published in the literature are too optimistic on how things can work. And I hope this can tell you how complicated is the problem and how large is the variability between cities, among cities. So there are certain cities where deprivation is clearly visible. Just the neighborhoods look different, even at just 10-meter resolution. And then you can get a decent accuracy. F1 score is like this. But look, they are ranked here by let's look at F1 score. You have cities where you have 21% of accuracy. People don't publish these results normally because they say, well, the reviewer, probably reviewers know nothing about the technical, about the problem, societal problem. They just look at numbers and they say, your method doesn't work well. It's not the method that doesn't work well, it's the problem that is complicated, right? And it's not that you develop a more powerful deep learning model and you will then bring it up to 90%. No, it's not that the problem. And I think we need to be transparent on this. The fact is that there are cities where there are not clear visible signs that allow you to distinguish. So the complexity is much more hidden. You don't see it in satellite images, right? But to be transparent, I think we need to know that this technology works sometimes, somewhere, not everywhere. We need to work on this, not try to improve the architecture and add 1,000 layers. That doesn't help here. Okay, trying to wrap up because we have the coffee break. Challenges, many. I think talked about several. But here, just to wrap up, the coarse resolution, the poor reference data quality. That's the biggest issue. And I say it in this particular application, but I would actually make a stronger argument that in many real applications, the real bottleneck is data quality. Is not the model, is not to define a better design, a more sophisticated model to get higher accuracy. It's the data quality that is the bottleneck. That means, I mean, that's again my perspective. You know, I'm not a pure machine learning person, right? A person that wants to see this applied to geospatial problems. And I realized after working more on the technical level for more than 10 years, I realized, okay, now it doesn't make sense for me to try to get 1% more accuracy on a certain benchmark. That doesn't bring me anywhere. Doesn't mean it's, I mean, there's still very valuable research that can be done there. But if you want to have an impact, and if you want to solve real problems, there are other challenges out there that we have to address, like, I don't know, data quality, for me, it's one, or making sure that what we design as researchers are then hitting real users and doing something that matters. So data quality, uncertainty quantification is something very important. Generalization ability, this typical, the challenge. You train in Salvador, you apply to Dar es Salaam, doesn't mean that that works, right? And the other thing I mentioned is, I think, what they call the shift from model-centric AI towards user and data-centric AI, right? That captures a bit what I mentioned. So not so much emphasis on designing the model itself, but looking at the whole workflow more holistically, and not just the deep learning technique. And okay, maybe last point, then let's all go for a coffee, is we are now working together with UN Habitat to actually design a new SDG indicator for slum mapping, and actually to possibly make a different definition of what is a slum based on what is observable from Earth observation data and what is not. So to make, and okay, I can tell you more if you're interested, but basically to go towards a more hierarchical definition of what we can capture depending on the data that is available. With Earth observation, you capture only some morphological characteristics of the slum. As you have seen from the results, in some cities works well, high accuracy, in some cities not, because these morphological characteristics are not the strongest predictor. So then you need to capture additional information, and that should come from other sources, not from satellite data. This part, it's a little bit more technical, so it's not really applied to a very specific SDG, but as I mentioned before, I think it's relevant for several applications, geospatial applications. So is the problem that, okay, here it's you see the title is about building outline extraction, but from a more general point of view, I see this as the topic of mapping buildings or other objects, potentially directly in a vector format. So the idea is to extract objects as polygons, directly usable in a vector, in a GIS software. It's relevant for several applications, right? So as mentioned before, because in a GIS, it's just a map. You can attach attributes to polygons, and this can be used for buildings, can be used for agricultural fields, can be used for cadastral boundaries, can be used for many applications. Whenever you need a map and you want to collect a database of information, and so on. So that's why it's very relevant. But now I will talk more specifically for building outline extraction. So building outline extraction, is a very typical application. You want to extract, and a typical thing that mapping agency have to do. And in my experience, official mapping agencies still do this exercise as a manual job. That's how this is done officially in the Netherlands by mapping agencies. So I think there is still work to be done to push the results of research community, what we publish, to reach end users. But anyway, what is the challenge? If you use also the latest developments in convolutional networks, deep learning techniques, and so on, most of these techniques, if you try to map buildings, you end up with results that look a little bit like this. Which means the typically rounded corners, not straight edges and corners. And that's kind of a typical result. And then, from the research point of view, people just publish and they say, well, I have an intersection over union of 98%. I have very good result. If you look at this, I don't know, maybe the specific result, actually the intersection of a union, it's really very high. It's a very good result. Nothing to complain if you look at this using a raster-based metric. But then you go to a mapping agency and you tell, well, I have this model and gives 98% of accuracy, so it's really good. And then they look at the results and they say, well, but this is not something I can use. I cannot just take this and throw it in my official layer of building outlines. It just has to be manually corrected, and it's a lot of work. And then they tell you, well, I prefer just to do it from scratch. It's just faster. And that's still the biggest challenge. And the biggest challenge, if you want to make use of this, is really to fill that gap. And if people don't maybe all understand that this 2% is not the big issue, but there is another issue in the data quality. So just to make a long story short, what we try to design are deep learning techniques that can potentially directly predict polygon outputs of objects with regularized geometries. So buildings, we expect, in most of the cases, have a relatively regular geometry, straight corners and edges. That doesn't apply if you want to do it for field boundaries, doesn't apply if you do other types of objects. But for buildings, that's the case. A special case could be about road extraction. where you have also typically different geometry. But let's for now focus on buildings. So this was a work done by a PhD student, Wufan Chao. A few years ago, we started working on this idea. There are several other groups, of course, that are working on this. And what Wufan designed, again, this is a few years ago, is a deep learning strategy that takes raster images as input and predicts polygons, predict location of individual vertices and closed polygons. So there are nowadays actually several techniques out there. So it's quite, it's a topic now you find also several papers also in computer vision about this topic. So what we designed at that time, Wufan, was this technique. I will not explain all the detail of this architecture. It's a bit complicated, but just try to give the intuition behind that. So there is a convolutional network. It's an encoder-decoder structure. Resemble a little bit the idea of UNet, if you have seen it yesterday. But basically, convolutional networks are very good in capturing the spatial information, and they're good in detecting edges and corners. So if you can detect accurately where the corners are located, then you can say, okay, these are the vertices that in the end will make up the polygon. But that's typically not enough. You just don't want to know just where are the vertices. You need to know how to connect them. You need to connect them in the right sequence so that you close the polygon properly. So that's why after this, there was another module, which is a recurrent neural network that basically learns the sequence of these vertices and learns how to connect one by one. So basically, for each vertex, has to know which one is the next one, so then you can connect all of them. So this was the approach that we used at that time, and in principle gives you directly polygons of building outlines. So these are just some qualitative examples. This is a reference. This is mask RCNN, was one of the first techniques for instance segmentation. I'm not sure if you're familiar with instance segmentation. Some are nodding, some not. So I guess you know semantic segmentation, right? Semantic segmentation, each pixel, you assign a label of what kind of line cover is, what kind of object. But suppose you apply this to building, right? You would have a binary output where you have, I don't know, 0 for everything else and 1 for buildings, right? But you don't distinguish individual buildings. You just have the map of the buildings. But suppose you want to count how many buildings you have there, you cannot do it from a semantic segmentation map. So in instance segmentation, also assign different labels to individual instances of the object, right? So then you have the ability to separate individual buildings. But it's still raster-based. So what we're actually doing here is, we could call it vector-based instance segmentation, right? So it's delineating individual buildings in a vector format. Good. It's I just showed this. It's a very interesting research direction. We're still working on that, and there are other papers, other methods out there for this application, and it's developing very quickly. So nowadays there are several other strategies out there. Want to mention another thing, which is another idea we had following up on this. So what we have seen so far, we can go from this to this. So we obtain a regularized polygon of the building outlines. We thought, okay, can we do one step further and also get more detailed information about the roof structure of that building? So one can ask, okay, under the assumption that most buildings are based with or composed of planes, so you can identify the linear planes within the roof. So you would end up with something like this, where you identify and detect individual planes that make up the roof structure. And that's quite interesting because this object that we want to predict is then a graph, it's not just a polygon anymore, and you need to identify where are the vertices and where are the links between these vertices to make up the geometrical structure of the rooftop. So this is also work done with WUFAN. And again, I will not go too much into the technical details. I'll try to very, at high level, describe a little bit how this technique work. So basically there is a feature extraction part, there's a backbone that extract where are the line segments, where are the vertices. And I skip all these little things in here, but basically once you have the line segments, you need to learn from the data, you need to learn how to connect them and understand where there is a link between them. And that's done by this part. It's a graph convolutional network that learns the graph that describes the connections between line segments. And you can think of it as a matrix, a junction adjacency matrix. If you have all the rows and columns that are different vertices, in practice it's done with line segments, but I think it's easier to think that so you have a number of columns equal to the number of nodes or vertices, then in the matrix tells which this node is connected to which other nodes. So if you know where are the connections, then you can reconstruct the topology of the rooftop. Yeah, make sense? So that's a little bit of the idea, and that's what we have implemented, and we have also tested on some benchmark data sets. So the idea is indeed you take your image and you directly predict the graph in a vector format that describes the rooftop geometry. And comparison with different methods. So I only have qualitative results here. If you look at the paper, you see all the numbers as well. It's just to a little bit give you the idea, and this is a little bit what we can do in the future with this. Potentially, if you have very high resolution images, in the Netherlands we have openly available aerial images at 8 centimeter resolution. It's huge for the whole data set, for the whole country, and other countries as well. So what you can do is actually try to map buildings, map their geometry, and if you actually combine this is still 2D data, right? The roof structure, and you have a digital elevation model, so you have also the height, then you can extrude the structure and actually create a 3D model of cities. So that's a little bit the direction, is to combine these different data sources. Actually, one can use images and LiDAR point cloud, integrate this data set. It's not simple. That's why it's future, something still to be explored. There are methods out there for doing this, but as far as I know, they don't do this directly in a vector format. So there are still challenges there. But that can be, I think, a very interesting future development. And then goes back to the idea of building digital twin models for cities where you have an accurate geometrical representation, and then you combine with other data collected on the ground, sensor networks, and so on. Questions? Are there any questions about this part? Yeah?
When you talk about digital twin, like a city has a lot of features, like not only buildings, trees, and so many things, like boats, especially in India. I'm from India, especially from Bangalore. And we have a lot of, it's a complex. So how you will be generalize the model from the developed city or
Yeah.
the developing city? And how this is only building extraction. So when you look into the tree extraction or any other features, how you can combine together
Yeah, yeah. No, of course. So creating a full 3D model of a city is much more complicated than this. I mean, this is already complicated, but to do fully automatic, all the objects in the city, including trees, I don't know, water body, whatever else is in a city, requires much more work. And also to consider that not all objects have these characteristics, right, geometrically. So for trees, you cannot use this approach. You would have to use something else. Geometry is totally different.
Is it possible to integrate also? It's not.
Yeah, I guess one can actually use multiple components, right? So this would work for buildings. Then you could have other modules, maybe specific for roads, for trees, vegetation, and other objects. Okay, yeah. And yeah, we currently have a project and another PhD student which is working on extracting and automatically updating the topographic map of the Netherlands. So that's, again, is fully open. And the topographic map has several objects defined, more than 20 different objects, including roads, buildings, bridges, water bodies, everything. So it's very detailed. And it's all in a vector format, right? And currently done, as I said before, manually, right? So the idea of this project is now to design deep learning strategies that could directly predict the topographic map. Still, this is 2D. It's not this 3D. That's another thing. Still 2D, but the 2D is already challenging enough to do this in an automated way. Yeah.
Before I worked with a product that's similar to this, and in Australia, aerial imagery, they try to extract 6 features from an aerial map.
Mm-hmm.
Building expands is one of them. And one major challenge we have is the flight angle. When it is not naive,
Yeah.
it is on a very oblique view, it usually overestimate the area and it go to the next best part.
Yeah, true.
Do you correct those angle feature or like it's just coming from the source of data is not good enough and nothing can
Yeah, yeah, yeah. There are many issues. This is definitely one of them, the viewing angle. I think in our case, we can correct at least part of this geometrical distortions and reconstruct a true orthophoto. So that's in principle. So then would mitigate the problem that you just described. Then you have other problems. You have shadows and the other ones. So also what we can do from images, it's a view from above, and that's why I said outline of buildings. But if you talk to people really in cadastre or mapping agencies, they say, well, we need to have the footprint. And sometimes the roof, it's larger than the footprint itself. Well, that's another problem. We cannot do much, so you can only, from above, you only see the outline, but you don't know the footprint exactly. So these are all practical problems that, need to be somehow addressed. Other comments, questions? Then move on. This is actually about tenure security. I mentioned that in the beginning. Why is it so important, tenure security? And is actually mentioned in several parts of the agenda. So several of the SDG targets contain in one way or another something about tenure security. The reason is that currently only about 30% of the global population has legally registered rights to their land and homes. And why is this an issue? You can imagine, but just to be clear, several things, several effects of this tenure insecurity that often result in poverty and endless legal problems. In fact, by not having registered rights, you typically can have legal conflicts between your neighbors and so on. And this has an impact to several of the problems I mentioned before, right? So for slum mapping, of course, there is an issue that some of the people living in these houses, they don't have legal registered rights. It can also be linked to farmers and small-scale smallholder farmers when they don't have legally registered rights for their land. And that brings the challenges I mentioned before. So they don't have access to financial and insurance services. That's often a problem. So there is a number of consequences by not having a well-established land administration system that often results in many issues at country level. And results in, yes, an equal economic system and so on. So in particular, so all this SDG mentioned tenure security, and in particular the target 1.4 that aims to provide tenure security for all, including minor groups and so on. So it's a societal problem. What can we do with remote sensing? We can do something about this. I'm not telling you we can magically solve everything. It's a very complicated problem. But we can do something. And so the concept of fit-for-purpose land administration have been designed, developed. The idea of fit-for-purpose land administration is to use satellite, aerial images to speed up the process of collecting these cadastral boundaries. It's a difficult task, and that's not typically how it is done in most of the country. So in most of the country, cadastral boundaries are collected by field surveys with traditional surveying tools, with GRSS system, theodolites, precise measurements of the parcels, and so on. It has been estimated that if we want to obtain a full cadastral land administration system in Africa, this can take several centuries. So it's very expensive, it's very time-consuming, and that's why the idea of using Earth observation. Not to fully extract everything. Why? Well, because not all cadastral boundaries are necessarily visible. And what I say visible, I mean that there is an object that delimits one property from another. In some cases, they are just cadastral boundaries that are just drawn on a map, and there is no object in there that actually separate the two properties. So what we do is to separate what we call visible cadastral boundaries from the invisible boundaries. And we can hope to extract the visible boundaries from images, but the invisible one is probably mission impossible. Okay, but the idea is at least we can extract the visible, hopefully, and then maybe a semi-automated strategy can help and speed up the process and collect all the cadastral boundaries. So we have done some studies. So this was a study from a master student a few years ago that applied this to two study areas in Rwanda. And by the way, these examples are also based on Horizon project that a colleague of mine was leading, which was really aiming at automatizing the process of collecting cadastral boundaries in several African countries. Using, in this case, was not satellite data, was UAV images, so much higher resolution. So of course, in these cases, you can see fences, you can see some objects that can delimit the different properties, and we can use that information to detect the boundaries. So these are just visually some results. You see the reference on the left. I'm not sure if you can see, it's not very clear, but we also try to distinguish. So the boundaries in green are what we consider visible boundaries, and the red are the invisible ones. And then you see on the second column the boundaries predicted by a convolutional network. It's pretty sparse, so it's not really complete, but it tends to agree pretty well on the visible boundaries. So the precision, it's okay, but it misses a lot of boundaries, that's clear. The other two columns are some segmentation techniques that were used in the past in the literature, but so what you see is you have a lot of false boundaries. They are just segments, but they are not associated to cadastral boundaries at all. So in a way, the second result is potentially more useful, even if it's very incomplete, but it's the starting point to then being manually corrected and completed. Another study by another student done in Ethiopia. They've launched this program aiming at registering rural land. So a program to use also different types of information to collect all these cadastral boundaries. They have collected aerial and UAV images in this area, and my student then did some tests using both aerial and UAV images of different resolution. In this case, we had actually the official cadastral boundaries. So this is the official governmental information, and we use this to train and test deep learning model. Technique is based on UNet, and actually then we used another approach. I didn't explain, but it's one other technique for extracting polygons out of raster images. It's called frame field learning. I'm afraid I missed to put a reference in here. Yeah, that's a pity, but if you Google frame field learning, you will find the reference. It's not my work. It's from colleagues from France. But anyway, it's a UNet strategy, so that it's trying to predict the edges and also the interior of the mask of an object, or the parcel. And on top of that has what's called the frame field, is actually providing information about the orientation of the edges. And this is typically very helpful in the polygonization step, and helps also in detecting more precisely where the corners are. So we apply this method to both the UAV and the aerial image, and we then calculated the accuracy using both MIOU, so intersection, the average or the mean intersection over union, and also the polis metric I mentioned before. So these are some of the visuals of the results that we obtained. Again, it's not really perfect, but I think it's a promising direction. And one of the big challenges, as for other studies I mentioned before, is that there are very few benchmark data sets for cadastral boundary. It's typically a bit of a niche in Earth observation. That's why we decided to build a benchmark data set for people to really work on this. And we started from a country where there is plenty of data, and that's the Netherlands, with the idea of then moving towards data-scarce countries where this information is not there. And because, of course, replicating this in the Netherlands might seem not so useful, and indeed maybe it's not that useful, but it can still be useful because these cadastral maps are there, but it needs to be updated every time. So it's still a technology which is valuable. And the other point is often, because when I talk about this, yes, but they ask me, yes, but how many of these boundaries are actually visible boundaries? And I say, well, we don't know, depends on many things. I usually couldn't give a precise answer. And then I said, okay, let's try to give a precise answer, at least for the Netherlands. And in the Netherlands, we have open data for the cadastral boundaries. So we have the official cadastral boundaries for the whole country, but we also have the topographic map for the whole country. It's all open. Topographic map, just to clarify, it's not about a relief map, because sometimes that generates confusion. It's basically a land cover land use map, very detailed, right? It has all the classes of the different objects. And basically, the topographic map, and not only one, there are actually several done at different scale. We put them all together. But basically, this map tells where are the objects on the ground. And then if you compare cadastral boundaries with boundaries of real objects on the ground that are mapped, then you know which one of these boundaries are visible because there is an object there, and which one are not. And that's what we did. We actually took a large sample, so these little squares are the tiles that we picked from the country. The different colors in this map are different landscape types. So we wanted to do some stratification over different types of landscape, including both urban and rural areas. And we did this, we developed a pipeline. When I say we, sorry, I just made this slide this morning very quickly. It's the work of Jeroen Grift, which is my PhD student, which is actually doing a PhD and working also at the Kadaster in the Netherlands, so the Dutch Kadaster. We did this comparison with some buffer, because of course you need to consider some buffer in the position of the boundaries and so on. You find all the details in the reference that I didn't put in there. I will give you later the reference. We finally came up with a number. So approximately 72% of all cadastral boundaries in the Netherlands are visible. So that's something nice. We know 72% are actually associated with physical objects on the ground. Of course, that doesn't tell, this is only for the Netherlands. In another country, you don't know. But now we have a large data set. We can use it to train model. We can test, and we can assess the accuracy, knowing also which of these boundaries are visible, which one are not. And possibly, we hope that models trained here can be transferred in other countries. That's the next step in the PhD work of Jeroen. Okay, actually that's kind of ends this topic on cadastral mapping. Are there any questions or comments here? Okay, then I'll move on. And this is finally my last topic for today. And I'm going to talk about glaciers and glacier mapping. I'm, as you see, moving from different areas in the world, from the hot of tropical areas to the cold of Arctic areas and so on. Why glaciers? Well, glaciers are really very important for climate change, are considered an essential variable for monitoring and modeling climate change. The retreat of glaciers are one of the major contributors to sea level rise. The major contributions comes from ice sheets. So just to be clear, typically glaciers, we don't consider ice sheets. We don't consider Antarctica, Greenland, but we consider only the glaciers. And the retreat also has a number of effects. So globally, sea level rise, but also locally. So they affect the local hydrology, the local ecosystem, and also potential risks at local level. When sometimes you hear in the news that people died because some parts of the glacier collapses and people are affected by that. So mapping glaciers is important for all these things that I've mentioned. And currently there is data on glaciers. There are more than 200,000 glaciers in the world, and they have in principle all been mapped, and all these inventories have been put together into this data set. It's called GLIMS. And basically, it's a combination of several different archives, and it's a complete database of glacier outlines. So here I'm talking about mapping, again, only 2D maps of the glacier outlines. However, there are, as usual, data quality issues. These are manually digitized by glaciologists, mostly looking at optical images, Landsat for most of them. And of course, subjectivity is part of the mapping because people are subjective and interpret things in different ways. But one of the biggest issue is they're incomplete in time. So we have probably for all glaciers at least one map. We don't know when in time. Some glaciers are mapped in 2000, some in 2010, some in 2020. But we cannot have a complete multi-temporal view if we want to understand how these glaciers are retreating over time if we have a sparse database. And mapping them and producing a map of all the glaciers potentially at a yearly basis, it's just not feasible because doing this manually, it's a huge amount of work. So that's what we try to do in this other project. It's called Massive, and it's done in collaboration with the University of Oslo and ITC and EURAC Research in Italy. And I'm not a glaciologist myself, so I'm not an expert in glaciers. But we collaborate with glaciology. In this case, it's Thomas Schellenberger from the University of Oslo and the group there. They know much more about glaciers than I do. I know a little bit about machine learning and Earth observation, and that's how we collaborate. And the idea of this project is to produce large-scale inventories of glacier outlines. That's the first thing. And next, actually, what we want to do, which is a much harder task, is also to estimate the surface mass balance. So it's really the most important than hydrological variable that we need to take into account to understand how glaciers are retreating. So it's not only to change in the area, but the change in mass that is important, volume and mass. But okay, for now we are focusing on fully automating the glacier mapping using deep learning. We want to achieve this mapping at global scale. So it's really huge, huge amount of data, several challenges, you can imagine, data quality, and we want to do this multi-temporally. That means we have some of these glaciers are mapped, as I said before, in different years, and we can go back in time, almost 40 years, using Landsat images, but then for different times, we need to use different sensors. So we have also to integrate different data, different sensors, all together into one model. So that's the work of Konstantin Maslov, my PhD student, together with Thomas, as I mentioned before, and Alfred Stein. So Konstantin made an amazing work. He put together a very large data set capturing the diversity of glaciers in the world, including Arctic area, Greenland, tropical, high mountain Asia, all the regions in the world. And the data set includes 9% of all glaciers worldwide. It's still huge. I believe it's more than 400 gigabytes of data. We plan to release the data. We just don't know where, because repository don't usually allow to upload such large data sets. So that's one of the challenges. The data is divided in tiles of approximately 10 by 10 kilometers. We have all these tiles. We can then split them in training, validation, and test. And then we can train different machine learning model, test them, and assess their accuracy. We use, so the work that you see here, it's currently under review. Hopefully will be published soon. But the preprint is out there, so the preprint you can read. We use different data tracks, which you see here, only optical data plus digital elevation model, optical plus DEM plus thermal bands, and also including SAR or in-SAR interferometric data. And let me see if I have more here. There could have been more to say. I actually realized in these slides I put only few things. In the paper you will see many more things. We also explored different type of deep learning strategy, different transfer or different strategies to reach global scale mapping. Because one of the other challenges, how do you make a model generalize so well that you can map glaciers in completely different parts of the world with completely different characteristics? So we explore different strategies. One can think of one global model for everything, or one can think, okay, I train local models, try to capture and divide the whole globe into glaciers of similar properties and have different models for different areas, or hybrid solutions where you have a global model and then you fine-tune it locally and things like this. So we have explored several of this strategy. You see all the details if you are interested in the work. Maybe one thing to mention, what is actually the challenge? So mapping clean ice of glaciers, it's not difficult. It's a relatively simple task. Actually, in the past, you could just compute some spectral indices, put a threshold, kind of work. But the real challenge is to map debris-covered glaciers. So many of these glaciers have rocks on top and have debris, and then you don't see the clean ice, and then it's very hard. And that actually the real challenge. I'm not sure okay, I had it in another presentation, but I can. So the problem is typically on the tongue of the glacier. So that area is typically covered by glacier. And why is it important to focus on there is also because that's where the area that's going to change over time, right? Because the tongue is the one where you see the retreat happening. So that's why it's very important to map these areas covered by debris properly. And then that's where deep learning, of course, can contribute, can help in getting better results. With challenges, but of course much better than traditional pixel-based strategies. What we did, so it's also something that's, I think it's not a standard practice in remote sensing. Maybe we can discuss. So typically, people in remote sensing, they have their data set. They divide in training, validation, and test. There is strong emphasis on saying, well, we want to have test that is independent and also spatially disjoint, not autocorrelated. I don't know if others have discussed this, but definitely that's very important. But our challenge, it's something that usually is not done because people say, okay, this is my data set, and the goal is to apply it to the test set. here the goal is not applying to the test set, but to develop a model that can be applied globally, and not on the data that is already there, but on future acquisitions. And future acquisitions might be done with different sensor than the one acquired in the past. So we've done, apart from a standard test set, we also used a test set from completely independent areas with different sensors. So it's also incorporating the generalization ability cross sensors, right? Because we train with data that combines optical data from different sensors, Landsat, Sentinel-2, and so on. SAR data, the same story. So one has to also try to test this kind of generalization ability. A little bit about the model. So this is it's called GLAVITU. It's a hybrid transformer CNN approach. I'm not sure if somebody in this summer school talked about transformers. No? Okay. Okay, it's advanced deep learning stuff, initially applied more to sequential data, especially to text data. We have nowadays also vision transformers that have shown, that have also very good properties also for image analysis tasks. And much could be said, but let me just try to summarize it. One of the main properties is the ability to learn self-attention and learn which parts of an image are contributed most to the prediction of the label. And it can help in capturing large distance spatial dependencies, right? So that's one thing of the CNN also does well, right? You have a patch and you capture all the spatial information. The transformer in principle can do it even better with the concept of self-attention mechanism. But anyway, the idea is that we combine the two. So there is a transformer in the first part. It can captures this long-range spatial dependencies. Then there is a convolutional network, a unit-like type of network. If you see, it's a little bit shallower. As I said before, we've done several tests. One doesn't need all this 5 downsampling layer and so on. And yeah, this has been fine-tuned. There is actually also a block here that fuses the different data sources. We are combining different optical, SAR, digital elevation models all together. All the details, again, in the paper. And maybe one thing to mention here, because it's a point raised before, it's uncertainty quantification. There are a few methods that one can use to do uncertainty quantification with neural networks. One way to do this is called Monte Carlo dropout. So the idea is you can think of, like, are you familiar with ensemble learning techniques? The idea is like you have not just one model, but kind of an ensemble of different models, or models that takes different views on the data, different subset of features, or different parts of the training set, and so on. So, and when you make prediction, you can actually not just make one prediction, you make a number of these predictions, and then you can use this to assess the uncertainties. So with Monte Carlo dropout, then you can actually derive probabilities for the predictions. And from these probabilities, you can derive a confidence measure. And then this confidence is something that tells you well, it tells you indeed how reliable is your prediction at a certain location, at a certain point. One thing that we have done in this work, and that is not commonly done in the literature, at least in the remote sensing literature, is to calibrate this confidence. So most work take this uncertainty or this confidence as it comes out from the model itself. And then that allows you to say which area, so if you produce a map, which area are predicted with higher confidence and which one with lower confidence. However, if you don't calibrate this, you cannot really relate this confidence with an expected accuracy of your model. So if you see this is the confidence as it comes out directly from this first equation. And one thing that one can do is you have a training set, we have a validation set. That's the one we typically use for hyperparameter tuning, right? But we can also use it to look at the pixels, the samples, and look what is the accuracy of those pixels. And we can plot the confidence with respect to the accuracy. And one would hope that these two are very nicely related, correlated with each other. But that's what comes out, that typically there is a relation, of course, it captures that information, but it's not really a nice, straight relationship. It's not a linear relationship. So by then applying a calibration, you kind of, we learn how to sort of optimize the confidence, applying a regression model that tries to stretch these confidence values in such a way that they correlate as much as possible with the actual accuracy. So we kind of normalize, we stretch these values, and then we know that when you have, I don't know, a certain confidence that, I don't know, is 0.7, I can interpret this number in sort of absolute terms. Because I can tell, well, if I have a 0.7 confidence, I expect to have, for all pixels, for all samples that have 0.7 confidence, I expect to have 70% of accuracy, right? That's what you would like to have, that your confidence is a proxy for the accuracy of your model. That's what you want to use in areas where you don't have the test set, right? So in an area where you don't have any data at all, you can look at your confidence, and then you have an idea of how well your model will perform exactly on those samples. And once you calibrate, actually then you can interpret the confidence exactly as a proxy of accuracy. Does it make sense? So that's the idea of this. So we have calibrated, and this is, as you see, how it looks. So actually you can see that above 0.5, there is actually a pretty strong linear relationship between the confidence and the accuracy. So in principle, it's a nice measure because we can use it. Suppose actually, that's what we want to do, right? We have trained this data, this model on this large amount of data, and we apply it on future acquisitions, so we can keep on mapping glaciers, where we don't have test set, because we would have to acquire new reference data every time, but we have calibrated confidence that we can use to assess how good is the prediction. Yeah? All the details, again, in the paper. Are there questions? Yes. It's still the same. It's still all in one very big paper. Yes, actually the name has changed. But if you look it up, you will find, because on archive you can have different versions. So the new version has a different title. Yeah, these are some results. And the nice thing, so you see different glacier tongues. You see so the yellow is the matched. So when reference and prediction match, so the boundary is correct. And when you see only green, means that's different. So then there is something wrong. And then the other thing is that we also show in these maps the confidence interval. Now, if we have a prediction of this confidence value, this confidence is calibrated, means sort of has absolute meaning, then we can also map the 95% confidence band. So around the outline, we can have a band that tells the area that falls within the 95% confidence interval. So then you see here the tongue, so the yellow is the prediction, and the red tells you this is area of still confusion potentially, right? So you expect, just to clarify maybe, that with 95% of probability, the true outline falls within this red band, right? That's how to interpret this. So you don't just show the outline as it is, but also the confidence around it. That's also not something, as far as I know, commonly done in remote sensing. So I think it's important, coming back to what I was telling before, that if you produce map automatically, can we also more transparently communicate the uncertainty of our models, so in the maps as well. Okay. There are lots of numerical results. So, and we also distinguish different kinds of model with different types of strategies for training and transferring the models. I don't think I can tell you everything about this table. What I remember is that clearly, maybe we can have a look also here. These are all different regions. I don't remember all by heart. So Alp is the Alps. That's what I remember. I think then, so all these are different regions. You see there is also quite some variability between different regions. Typically it's because clean eyes, so area with clean eyes is relatively easier to map. Debris covered is more difficult, and there are other challenges on ice melange, glaciers that are on coastal areas, the calving fronts, and all these things. But anyway, so all the details in the paper. Some final remarks. So one thing we tested, okay, I don't have results here, but there is a significant improvement using this deep learning strategy with respect to traditional machine learning model. We also compared to even more basic techniques based on just thresholds on spectral indices, and this performs significantly better. We also did additional tests in different areas where actually multiple people have delineated the same glacier. And now I cannot give you all the information, all the details, but this allowed us to also try to quantify what is also the uncertainty of manual delineation. And then we can say, what is the uncertainty of manual or human operators in delineating the glaciers and the one of automated methods? And then we could claim that we reach similar level of accuracy than human annotations with a scalable approach that can be applied large scale. I think that's pretty much all. So I finished even earlier, so I'm fine to stay here for questions. I have just a slide with some final conclusions, which are a little bit at high level. So I think I show some example where Earth observation, deep learning combined can contribute in extracting information in support of the Sustainable Development Goals, or in general of societal, environmental, global challenges. I believe that Earth observation combined with machine learning can contribute significantly towards the SDG, and much more has to be done to make sure that research results are in the end used by the organizations that actually report on the SDG, which are the national statistical offices. And beyond that, I think that it's not just using Earth observation for reporting on certain indicators, but potentially providing information which is valuable for decision making and is valuable for, yeah, that's typically what scientists say, okay, my job is just to provide information, and then it's, I don't know, the politicians, the policymakers make decision. But that's my view, but it's also very much the view of my faculty, is that scientists can and should probably try to be involved in real societal problem, not just to think in abstract and theoretical terms and develop methods, but actively contribute by collaborating with stakeholders, policymakers, and other organizations to make an impact in the real world and make research results affect people in need. So that's in general what I hope that we, and me, and but as a community can try to do more. It's a challenging problem, it's difficult, and here I just list a few of the challenges. So how to transform, research result in something operational, something that can be applied, something that is used in by real mapping agencies and national statistical offices and so on. Still, of course, well, not all organizations trust and would just take the results of AI methods and use these results, right? Because we have to first prove that AI produce trustworthy, reliable, accurate predictions. Data quality, again and again, I repeated this, it's an issue. And we know that for lots of these problems, data is really of poor quality, very poor quality. So my point is, let's report this transparently. Let's not just hide the problems under the carpet. Let's be honest, and let's make clear what the technology can do and what are the limits of the technology, and not just report results by cherry-picking locations where things work and leave out where it doesn't. If you want to move towards global applications, there are a lot of problems, data issues, making sure machine learning models generalize well. And I mentioned more for this last application for glaciers. It's difficult, but it's still much easier than, I don't know, mapping slums at the global level, right? You have seen the complexity level there is even much higher. But still, the generalization ability of models is very important if we want to get not just a local understanding of phenomena, but understand globally how these phenomena are occurring, how they are developing. Maybe there could be many other things to mention, but I can stop here and take questions and comments. Thank you.